Hello everyone. In this video we'll be discussing binomial coefficients, and there's actually quite a few different ways I could have actually started approaching this topic, but I'm just going to straight up say a binomial coefficient is just a coefficient of this binomial to a power. So binomial x plus y to some power k. So if you expand that out and you look at the coefficients of each of those terms, those are binomial coefficients. Now there's a lot of different ways I could go about beginning this conversation because there are a lot of different interpretations and applications of binomial coefficients. And the biggest one is how many different ways you can choose a certain amount of objects from a set of a certain size. So in fact here, our notation is kc0, kc1, kc2, all the way to kck. Now this is sometimes known as a combination when written like this. We'll actually mainly be using this notation though, which is an alternative, more mathematical notation. The above one's used mostly in probability or statistics class, but in a pure mathematics class you would use this notation. And the way you pronounce this is k choose 0, k choose 1, k choose 2, all the way up to k choose k. Now, the reason why I'm labeling them like this, starting from 0 and ending to k, is if you were to actually expand this out, you have to see it with some examples. So we'll see it right now when we actually consider this when k is 3, for example. But when you actually expand this out, you will get basically the powers of x running from 0 to k, and the powers from y in reverse running from k to 0. So in total, you can label the coefficients, counting them from the 0th one all the way up to the kth one, if that makes sense. So here, and again, the alternative notation here is 3 choose n. So here we're asked to find 3 choose n for n going from 0 to 3. And how we're going to do this is we're going to actually consider x plus y raised to the 3rd power and just expand this out. So it's x plus y multiplied by x plus y multiplied by x plus y, a total of 3 times. Now the reason why choosing comes to mind, how many ways you can choose let's say 0 of 3 things, is because when you actually expand this out, there's a total amount of different choices for x and for y. We'll see what I mean when we actually expand it out. So first I will, and there's a lot of ways we can do this, but let's multiply. The way I normally like to do is do 2 first and then to the second one, or to the 3rd one I should say. So maybe I can do it like that, or maybe we can do these last 2 first. Doesn't really matter, but let's do the last 2 first actually. So we have x times x, that's x squared. X times y is yx, and y times x is also yx. So I'll write that as x times y, but we'll get 2 of them. So xy for the first arc here, and then yx for this one, but that's another xy. So those combine to 2xy. And then plus y times y is y squared. So I'll actually combine these, if you don't mind, as 2xy. Okay. So now let's distribute the x and y here into this. Same idea, distribute x into each of these 3, and then y after the fact into each of those 3. So x times x squared is x cubed. X times 2xy is 2x squared y. X times that is xy squared. Now distributing y in, we get y squared, or I guess x squared y. And here, y times 2xy is 2xy squared, and y times y squared is y cubed. Now there are some things notice that combine here. We have an x squared y term and another x squared y term. The coefficients here are 1 and 2. Those combine to 3. So we have x cubed, 3x squared y. These two combined, these are the xy squared terms. The coefficients here are 1 and 2, which combine to 3xy squared. And then the last guy is y cubed. Okay? So the coefficients actually are the numbers in front, which are 1, 3, 3, and 1. And we just label them accordingly. So maybe I'll write it over here. We have 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. So 3 choose 0 is 1. 3 choose 1 is the second coefficient here, which is 3. 3 choose 2 is also 3, notice, and 3 choose 3 is 1. Okay. But now, let's try to think a little bit. Why does this, I guess why would this have to do with choosing, or I guess how does that have to do with choosing? Well, if you think of it here, this x cubed means we're choosing 3 x's of these. So how can you actually multiply x to x to x to have a total of 3 x's only and no y's? Well, there's only one way to choose 3 x's and no y's. Or I guess another way to think of that is choosing 0 of 3 x's. So, or 0 of 3 y's, I guess you could say. Maybe that's a better way of interpreting that. And in fact, it's kind of interesting because you can think of this as the other way as well, the other way around as well, which we'll kind of get into later on. But notice here, there's 3 x's but no y's. So how many ways can you choose no y's of this distribution? Again, it sounds a little funny, but there's only one way to do it. X times x times x. That's the only way to get 3 x's. What about to get 2 x's and 1 y? You can choose these 2 x's and this y, that's one way. You can choose these 2 x's and this y, that's another way. And then you can choose these 2 x's and this y, that's the third way. There's no other way to do that. What about 1 x and 2 y's? It's the same idea because this is of course symmetric. So you can pick 2 y's and 1 x in the middle, the first x and those 2 y's, or the first 2 y's and that last x. So 3 ways there. And there's only one way to choose 3 y's, just this one, this one, this one. So that's why it has to do with picking or with choosing, because we have this kind of idea when it comes to distribution. In fact, that's an alternative way we could have actually expanded this out and combined by just asking ourselves, if we're picking 3 of each of these things, how many ways can we do that? And, it basically gets into that idea. Now, when it comes to actually, selecting a certain amount of people, for example, so let's say you have like 3 people and we want to choose 2 of those 3 people. Well, let's say the people we have are person A, person B, and person C, okay? And we're choosing 2 of those 3 people to go on a trip or something. So we have 3 people and 2 people, we want to choose 2 of the 3 people. So we can say choose A and B, we can choose A and C, or we can choose B and C. And what's interesting here is that the slot method for counting doesn't necessarily work. Because notice, if you were to choose 3 people for person A, and 3 people also for person 2, I meant for person 1 for person 2. So here we have the choices A, B, and C. But there's this actual idea that once you choose one person, then the next person to be chosen is 1 person less. So we could say there's 3 people to choose from here and 2 people to choose from here, but that would amount to a total of 6 possibilities, when in reality there's only 3 possibilities. So why is that? Well, in fact, this idea has to do with the fact that we could have different permutations of these selections, and we would get the same selection. So what do I mean by that? BA, CA, and CB. Those are not accounted for here, but they would be accounted for this selection. Notice like this, there's a total of 6 different possibilities. But do we really care if we pick person A before person B or person B before person A? I mean, it depends on the context of the question. For example, if you're picking 2 people of 3, where one person's a photographer and the other person's the interviewer or something like that, then yeah, there's a total of 6 different possibilities. But if you're just selecting 2 people without categorizing them at all, then there's only 3 different ways to do that. So that would be 3 choose 2. Okay. So now what we're going to do is we're going to develop some relationship between, I guess, these binomial coefficients, depending what our power is, basically, and we'll see a very beautiful connection to something called Pascal's Triangle. So let's take a look at that right now. Okay, so here we stumbled upon this recurrence relation, which I admit is not very obvious given our definition of binomial coefficients. Now you have to kind of play around with the idea and play around with the notation to get this. Now, the first thing I kind of want to mention is that before I kind of had things a little backwards and wrote it as k choose n instead of n choose k. It's still valid, but the usual way is n is on top and k is down below. That doesn't really matter, but I just don't want to confuse versus how things are usually written. Like if you were to look at the book, for example, it will say n choose k instead of k choose n, but it's the same idea, right? N and k are just numbers, so it doesn't really matter what we call n or what we call k. Anyways, here I'm giving you this relation. So recurrence relation I never actually spoke of previously, but recurrence relation just means it's a relationship involving a variable and that same variable. So if I wanted to find 5 choose 3, for example, using this, I would probably need to find 4 choose something first, and then 5 choose this. So you kind of have to run through a few of them. So for example, we calculated in the last screen that 3 choose 2 is equal to 3. So if you kind of consider this as our n minus 1, then plugging that in here, we get 3 choose 2 was 3, plus 3 choose, well, I guess if this is 2, then that would have to be 3. Now 3 choose 3 ended up being 1. There's only one way to choose 3 of 3 things. So this is 1 and this was 3. So that means this will be 4. Now according to this relationship, this is n minus 1, so that means n would be 1 more than 3, which is 4. And this is the same as the larger one, which is 3. So 4 choose 3 is 4. But we want 5 choose 3, so if you kind of consider this relationship, 5 choose 3 is going to be the same as, let me erase this for space, 4 choose, I guess, 2, plus 4 choose 3. Now 4 choose 3 we just found, but again, we had to hop through this middleman, have to jump through some loops to get there. So that's the whole deal with the recurrent relationships. So we know this is 4 now. And now what does 4 choose 2? Now if you wanted to, you can do the whole ABC thing and actually count and figure out how many ways you can choose 2 of 4 objects. But we can also just kind of use our idea that what we know from 3's. So for example, 4 choose 2 would be 4 choose 1, or I guess 3 choose 1, my mistake, plus 3 choose 2. This is 3. This is 1. There's only, sorry, this is not 1. This is also 3. There's 3 ways to choose 1 of 3 things. You can choose 1 of each of them, basically. Okay. Right, so if you add those, you get 6. So this should be 10. Okay. So that's interesting, and it kind of shows the usage of that. But what actually will show that in a nicer format is Pascal's triangle. Now, the way I've done it here doesn't actually show why this is true. I'm just using this idea. If you go back to the expansion of things and how I expanded, if you don't remember, we did x plus y to the third. Let me erase this for space. And what we actually ended up doing is we expanded this as x plus y multiplied by x plus y squared. Now, x plus y squared expanded is x squared plus 2xy plus y squared. So these are actually the binomial coefficients for x plus y to the second power. And if you distribute this, notice we're actually just kind of, we're basically getting this idea out. Because here we have these binomial coefficients, 1, 2, and 1. And when you expand it out, you'll notice here you get 1x cubed. And for the x squared y, you get 1xy there, so that's 2. And then you have, let me see, it's x squared y. So it's 1x squared y there, 1x squared y here. So I guess you really get 2 here and 1 here. So it's 3x squared y. So really what we're doing is we're adding this one to this one, kind of. We're basically adding these two together, these two coefficients together. Similarly, for the xy squared, we have, let's see, we have an xy squared here, okay, that's 1, and we have an xy squared here, so that's 2. So add those, 1 and 2, that's 3. So you're really just adding these two coefficients together. So it's xy squared, not x squared y, sorry. So adding these two together, you get those. And then for the last one, we just get 1. So 1y cubed. So what we're building up is known as Pascal's triangle. So Pascal's triangle is 1 choose 1, or I guess, no, 1 choose 1. This would be like 0 choose 0. Sounds funny, but that's how it would be. And then this would be 1 choose 0. This would be 1 choose 1. This would be 2 choose 0. This would be 2 choose 1, and this would be 2 choose 2. And the pattern would continue like this. Now, of course, usually when you introduce Pascal's triangle, we don't actually do it with this choose notation, we just do it with the values, with the numbers. But I want to say now that anything choose itself, so let's say k choose k, for example, is always 1. Similarly, k choose 0 is also always 1. There's only one way to choose k from k things, select all of them, and there's only one way to choose 0 of k things, choose none of them. There's only one way to do each of those. So in fact, what that establishes actually is that all of these are just 1s. All of these are 1s. So in Pascal's triangle, what you really get with the values, the value interpretation of Pascal's triangle that is you get 1s as borders of this triangle. So the 1s border this triangle like this. Then, according to this recurrence relationship that we've developed, kind of based on that idea of expansion, so I think that kind of actually more or less explains why the recurrence relation is true. You will just add these two above to get the one below and middle, add these two to get this one, add these two to get 4, 3 plus 3 is 6, 3 plus 1 is 4, and then now we get 1 plus 4 is 5, that's 10, 6 plus 4 is 10, 4 plus 1 is 5. We can keep going on and on and on and get all of these binomial coefficients. Perfect. Now, the way to kind of see this is if you wanted to find 5 choose 3, you would go to the 5th layer of Pascal's triangle, where this is the 0th layer, the 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th layer. So the layer is just the thing that has that number after the 1. And notice there's a lot of symmetry here. So in fact, I kind of mentioned this earlier, that it's the amount of way you can pick x's or no y's, or I said something like that. In fact, there is symmetry because x plus y is the same as y plus x. So you literally just get these coefficients in reverse as well. So if you look at this line of symmetry, you end up getting that. In fact, there's a lot of different patterns of Pascal's triangle. That's just one of them. Another short mention, I think, is that if you add all of the powers in, or all of the coefficients in a given layer, you get a power of 2. You get that power of 2, in fact. So if you add these, you get, well, you would get 2 to the 5th. And that's not very hard to show, or not hard to explain, I don't think, because these are the coefficients of x plus y to the 5th, right? So if you have x and y being 1, then you would just be adding the coefficients only, because any power of 1 is just 1. So you just get a sum of the coefficients. So the sum of the coefficients is just 1 plus 1, which is 2 to that power. So 2 to the 5th would be the sum of these, for example, which is 32. And you can see it's 20, it's 10, so it's 30, and then plus those 1s, you get 32 indeed. But now to calculate 5 choose 3 quickly, you can go to the 5th layer of Pascal's triangle here, and then start at 0, so that'd be 0, 1, 2, 3. 0, 1, 2, 3. So you always start with 0. That's the kind of key trick there. So that explains that 5 choose 3 is 10 using Pascal's triangle. And the great thing about Pascal's triangle is now we can expand x plus y to the 5th out if we wanted. It'd be this x to the 5th plus this times x to the 4th y plus this times x to the 2nd y to the 3rd, and you kind of go from there. So what happens is the powers of x decrease from 5 to 0, and the powers of y at the same time increase from 0 to 5 power. So that's kind of interesting, and that is known as the Binomial Theorem, which I don't actually really think it's too big of a deal if I don't write that down. There is also a really nice formula for these binomial coefficients that we don't really need to discuss right now, but I feel like I owe it to write it in this video. So I'll actually, I'll do this. We'll end this screen, and then the next screen we'll actually write out the binomial theorem, and then also that formula to how to calculate binomial coefficients. Okay, so finally we have these last two ideas, the binomial theorem and this formula for actually finding a binomial coefficient. So binomial theorem here says if you have x plus y to the n, then it's just the sum, so I don't know if you've seen this symbol before, sigma from k equals 0 to n of n choose k times x to the n minus k times y to the k. Basically, when k is 0, we start at x to the n and y to the 0. But when k is equal to n, then you have x to the n minus n, which is x to the 0, which is 1, and then y to the n. In other words, x goes from n down to 0, n and minus 1 and minus 2, all the way down to 0 with each term. And y starts from y to the 0 to y to the 1 to y to the 2, all the way up to y to the n. And the coefficients are just the binomial coefficient we saw. So here we're going to actually expand x plus 2 to the 4th, but using our newly found idea of Pascal's triangle. So I know, and also using binomial theorem, this is going to be something times x to the 4th times 2 to the 0, plus something times x to the 3rd, 2 to the 1, plus something times x to the 2nd, 2 to the 2. So we see how this is working, right? The power of x is decreasing as the power of 2 increases. So then we have, maybe I should have written it actually here just for space. So we have something times this, something times this, something times this guy. Okay, so now we're caught up. Now we have plus something times x to the 1, 2 to the 3, and then something else times x to the 0, 2 to the 4. Now the interesting thing to notice here is that all of these powers, if you get confused, all of these powers will each add up to 4 at a time. 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and 0 plus 4, of course, is 4. So I'm actually going to erase this line here because I've written it down below, so that's fine. But now how do we find these coefficients? Well, we know what they are based on Pascal's triangle. So if we go up to the 4th layer of Pascal's triangle, let's do it here in this space, I guess. We have 1, 1, 1, 1, 1, 2, 1, 1, 2, 1, 1, 3, 3, 1, and then finally here we have 1, 4, 6, 4, 1. So these are our coefficients we're looking for. This is the 4th layer of Pascal's triangle. So the numbers are 1, 4, 6, 4, and 1. So simplifying a bit, we get x to the 4th. That's 8x to the 3rd. That's 4 times 6 is 24, x to the 2nd. That's 8 times 4 is 32, x to the 1, and then 2 to the 4th is 16. So that's a lot quicker, a whole lot quicker than actually expanding it out, x plus 2 multiplied by itself 4 times. You can do it that way to just ensure that this indeed checks out. So now the formula I have to calculate the binomial coefficient is given by this. So this is kind of like a repeated multiplication from a number and its predecessor or its successor. So in other words, the next integer or the previous integer, just kind of depending. So notice with all of these binomial coefficients, n is larger than k, always. K could be equal to n, but n is larger than k. So what we're going to do is we're going to start with a large number on top and multiply it to all of the integers before that number up until the one before taking away this amount, taking away k. So the way it works is you count how many you have. So I'll show here with this example. We want to start with the number 10, and notice we're dividing by 1 times 2 times 3 all the way up to the bottom number in the bottom. So this is going to be 1, 2, 3, 4, 5, 6. So something that's not apparent here is that they're the same amount. So here these kind of coincide, these coincide, these coincide, and these coincide. So that means we're going to have 10, we're going to have 6 of these starting with 10 when you decrease. So decreasing 10 and multiplying those, we get 9 times 8 times 7 times 6 times 5. That's how that works. You decrease until you get caught up to the denominator number. So this is descending and this is ascending. So decreasing and increasing multiplication. And then from here, you witness any cross cancellation, or any, I guess, cancellation. So notice the 5's cancel. The 6's cancel. And in fact, you know what's funny is that we're always left with an integer, even though I've written this as a fraction, kind of in fraction formatting. So I'm going to say 2 times 4 is 8. 3 goes into 9 3 times. All we're left with on top is 10 times 3 times 7, which is 21 times 10, which is 210. Perfect. Without the need of Pascal's triangle, but, well, you'd have to do this for, I guess, all of the 11 different ones, different possibilities for the bottom one, 0 to 10, to find the entire layer of the 10th layer of Pascal's triangle. So the benefit of Pascal's triangle opposed to this formula is this formula only gives you one of them, where Pascal's triangle gives you all of them in that entire layer. So they have their pros and cons, of course, but this definitely is nice. Now, in the next sections, we'll actually be seeing different iterations of this formula, different ways of writing this, using what is known as factorial, which this basically describes that. But I'm getting ahead of myself. We'll see that in the next videos. So with that being said, I thank you all for watching. That ends our discussion here on binomial coefficients. Hope you enjoyed, and I'll see you in the next video.